Hamid, you're on.
Sure. Thank you, Henry. Can you see my slides?
Yeah.
Great. So sounds great. Hi, everyone. It is great to participate in this forum and learn about the exciting research on cybersecurity by the Stevens faculty. Our research at the Safe Autonomous Systems lab lies at the intersection of control theory and applications in unmanned aerial vehicles, also called drones. And for the last few years, I've been studying some of the emerging challenges in this area, such as cyber physical security and safe autonomy within the context of this control theory and unmanned aerial vehicles. My today's talk focuses on defending against cyber physical attacks by developing novel estimation and control algorithms, as well as new system architectures. Cyber physical systems are defined by seamless integration of physical component, computational elements through sensors, actuators, feedback loops, and communication links. So for example, smart grids, industrial plants, and new technologies such as surgical robots, self-driving cars, or network of commercial drones are all examples of CPS and complex CPS. So these systems are susceptible to sophisticated attack surfaces, which can originate from this software, sensors, actuators, communication network, or combination of all of these attack surfaces, right? So, and in fact, coordinated cyber physical attacks are on the top of the list of the Department of Homeland Security. So traditionally, the software verification methods and cybersecurity technologies have dealt with software attacks and failures. From the other hand, uncertainties in the physical systems are addressed mainly by fault-tolerant control methods. So however, each of these approaches fall short when it comes to the security of cyber-physical systems. And one addresses the software failures, while the other one requires accurate model of the physical system, which may be may not be available because of the uncertain world we are dealing with. So there is a need to bridge the gap between control and software verification methods for better understanding of CPS security. So this diagram summarizes our framework for attack resilient control of CPS. And the system under consideration in this diagram particularly is a UAV, unmanned aerial vehicle. And our diagram is based on the Simplex architecture, and we have extended this design to allow for multiple point of adaptation, and also be able to do the online system identification and identify the failure modes. So it consists of three main components. So the first component is the normal control environment, which runs the software for normal operation of the system. And there is a high assurance control environment, which is a bank of controllers and planners, which can be configured to adapt to different failure modes, right? And the third component of this diagram or architecture is the monitoring and capability auditing, which uses physics-based estimation along with program behavior monitoring to detect cyber physical attacks and failure and identify the different failure modes, right? So, and this example shows particularly applies to the drone when we have global missions, trajectories, path following, and autopilot controllers. So there are different types of cyber physical attacks has been reported recently, such as replay attacks, covert attacks, denial of service, and so on. Particularly, we have focused on stealth zero dynamic attacks. The interesting feature of these zero dynamic attacks is that one can devise an exponentially expanding signal at the input of the system while it remains undetected at the output. And this is usually the case for the system which we are dealing with. We have some few output measurement, but usually we have more states for the system. So if the attacker knows the model of the system, can calculate and inject the attack signal, which destabilizes the internal states, but while it does not show or has a minimum effect on the measured output, so it remains undetected, right? One way to deal with this attack is that to change the dynamics. So that's one way we try to use inducing the change in the dynamics to be able to reveal zero dynamic attacks. So particularly we use multi-rate sampling, as you see, for example, if you have an unbounded signal, and if you decide to sample it with the same rate, you collect this red line, which can remain zero, but while the continuous state of the system is expanding. So, we actually tested this multi-rate detection and control approach using a small crazy flight quadcopter. So here is the diagram, shows the flight test setup. The position of the drone is tracked by a motion capture system, and roll PCR commands are sent to the drone via a radio link. So, so here is this video shows the one of our tests. Here you can see the attack signal here. And the drone here tries to follow a sinusoidal trajectory, and we injected this, calculated and injected this zero dynamic attacks on that. And due to this attack, drone is perturbed, right? So we were able to timely detect and switch to the safety backup controller to be able to maintain the flight stability here. And here is another example. Actually, we compared the multi-rate sampling, detection and control versus a single rate or uniform rate. And we injected this attack signal on the roll and PCR commands, which we sent it to the drone, right? So on the left, you can see that the drone crashes, but on the right, after some perturbation, it can get back to the flight. So the important point is that for the CPS, we need to have a very timely detection to be able to recover from attack. And the same applies for the self-driving cars and so on. We also studied zero dynamic attacks when we have a system of multiple autonomous agents that communicate with each other over the network of for some coordinated tasks. One example of module agent system is this robots in the warehouse, right? So, for this problem, we formulated the problem as a second order consensus problem, a very simplified mathematical model. And we consider the case to specify a few agents as a monitoring agents, and with changing the network topology, we induce that dynamic change which allows us to detect a stealthy attack. And we did so by keeping this overall system partially observable, because usually there is a trade-off between the detection and privacy, right? So partial observability of this system, we can show that means that we can maintain the privacy. That means that if the attacker intercepts this information, is not able to reconstruct all the state of the distributed agents. So that's the important consideration. And currently we are working on sort of control monitoring approaches that are more scalable and are suitable for distributed systems with possibly heterogeneous systems. We consider a layered structure where we have a local and centralized observers, and also we divide agents into clusters. So here it helps us to be able to add in more agents and be able to sort of specify systematic ways to distribute and allocate observers. And we are looking into how to distribute the observers and share data, whether locally or globally, to be able to detect attacks while maintaining the privacy. And I guess that's all. Actually, at the end, I would add that the cybersecurity is a very multidisciplinary area. And I would like to, looking forward to collaborate with our colleagues at the Stevens and other schools in this area. Thank you.